Hey, I'm Zach Reynolds, and I'm here with Kat Olson and Nathan Smith, and we're going to talk a little bit about sustainable water collection. So, our student learning challenge, our team wanted to work towards a method of conserving water in agricultural and horticultural environments. In our original research, we had found that 70% of global water usage goes to agriculture. Our original goal was to try and implement incremental innovation to increase the sustainability of current agricultural methods. So a little bit about our methodology was based on the Renaissance Foundry model. So the Renaissance Foundry model is a method utilizing iterations in the learning process to advance understanding. Our group used the 6 steps associated with this to develop our prototype. They're listed below. So our actual iterative process, our group started off with the idea to design an irrigation system based off the center pivot irrigation with remote pH, moisture, and salinity sensors. So we actually decided to scale down to just our apparatus, and then we scaled down once again to go for more of a horticultural approach. We also had some 3D models printed off of the surface of our apparatus that showed our surface at different scales. We also wanted to point out that our apparatus is able to scale to not only the horticultural community, but also back up to agricultural and even commercial residences.
Hi, I'm Nathan Smith, and I'm going to introduce us to our prototype/solution to our student learning challenge. We designed a prototype atmospheric water condenser for use in greenhouses. While it also has a bunch of different uses in a larger scale or completely different applications, we decided to focus in on the horticultural aspect of it to easily model and show the detail of our prototype. While it can be applied to many different larger scale applications or anything completely different, we just decided to stick with this whole thing and get our foundation settled with it. The spark that led us to this solution is the darkling beetle, which can condense 40% of its body weight in water every day. We'll talk about that more in the next slide coming up in a second. While the focus of our prototype was to help conserve water in agriculture setting, it could also be used in a survival situation for clean water. It could be used as a good water management tool in urban or suburban environments. And now we're going to move on to our biomimicry inspiration, the darkling beetle of the Namib Desert. The darkling beetle is incredibly efficient at condensing atmospheric water, and it's able to condense 40% of its body weight in water per day. The reason it can do this is the ridges along its elytra, which are able to condense and direct water towards its mouth. This is because the points on the surface of the beetle have hydrophilic sections, while the rest of the beetle's shell is hydrophobic in nature, which directs the water towards its mouth. Here we have our fluid mechanics, where we use Bernoulli's principle to model the velocity of our fluid, the continuity of mass, which is our water condensated in minus our water out to water plants, and our Schwalter methodology, which models our flow regime as it's going down the pipe. Now, the optimal contact angle for aluminum is 4.6 degrees, which our prototype roughly equals. This means that it's an extremely hydrophilic surface, which allows it to condense lots of water all the time. And the reason it can do this is because the water will build up on its surface and the surface tension will break and it will flow off onto our hydrophobic surface and down into our system.
So the great thing about this apparatus is that it can be fully scaled depending on the size of the area of operation. This will depend on the size of the greenhouse that is wanted, and it can be upscaled to meet a large industrial greenhouse of any sort. The texture depths will stay the same for every model. Only greater dimensions of the entire model will need to be customized for a specific space. Materials to be used for the apparatus include the aluminum and the PET. This can be seen with this design. The PET resin will be in the middle part of this entire apparatus. Aluminum will be on either side, either acting as a structure of the material or as the little hydrophilic dots on the surface of this material. This SWOT analysis explains this product in detail with the strengths and the weaknesses of this product. The strengths include how it's scalable and inexpensive. The weaknesses include how there is little existing experimental data on it, and lots of funding will be needed to further investigate this new product. We would like to thank all of these people for helping us throughout the class and throughout this project, and we would like to thank you for listening to our presentation today. And here are all of our resources.